We're continuing with the notes. This is the top of page 46. So we're going to look at those ligands that are really carbon-based, starting with your 801 alkyl. So 801 alkyls. Now, in this case here, you're always talking about a negative charge on your 801 alkyl. So just to give you an example of one, so for example, a metal methyl, okay, or some form of CR3. That would be an alkyl, an 801, because it's only attached through one. So you're always talking about something with a negative charge. So when you're doing your electron counting, these would be 2 electron donors. Okay. Also in this category would be metal alkenes. Oops, spelling properly. You can have metal alkynes, and you can also have the metal aryls, which you're used to. These would be like your phenyl groups. So now, an important thing about metal alkyls, you're going to have the common ones and the not so common ones. So there's some that are rather unstable. Anything with a beta hydrogen is not as stable. So what I mean by a beta hydrogen, let's say you have, okay, CH2, C, and I'm actually going to put the H's on here. And then I'll just continue that as R. Okay. These H's here, those are beta hydrides there. So what can happen, I'm not going to draw everything out here. I'm just going to draw the important bits that we're looking at. What ends up happening is that you end up, it's a little situation where you can form what's called a beta elimination. Okay, so what can happen in here is you end up with electron rearrangement, and you end up kicking out, forming a new double metal bond here, breaking this one, breaking that one, and forming a metal hydride. So beta hydrides are not, or any compound that has a beta hydride is not that stable due to this mechanism. We're going to look more at these a little bit later. So some of the more common ones, I'll just write a little bit of a list here. So the more stable ones, you have stuff like phenyl, so C6H5. This one, which is nice, is the neopentyl. Yeah, that. So this is called neopentyl. Okay. You can read my handwriting, so it's a little small on here. It's another good one. Oh, yes. See, this doesn't have a beta hydrogen because this is the beta carbon and it has methyl groups on each of those. So you don't have that kind of instability. And this one also doesn't have a beta hydrogen. So this will be trimethyl silomethyl. Pretty long name for that. And of course, CH2, and then bound to your phenyl ring. So this is benzyl. Okay, also no beta hydrogens in that one either. All right, so let's move on to 802 alkenes. Now, in this case here, so we're talking about the double bonded carbons and how they can bind to a metal center. So like we're talking about something like this, okay? Now, there are a few pictures in your notes, and I wonder, I might open up a screenshot of this. So the first case is showing you the sigma donation. Let me see if I can share my screen here with you guys. And where did it go? There we go. Sorry, I had this all pulled up. Here we go. This is a good one. So if you guys can see my screen here, down here, this is showing us a sigma donation. So you have that pi bond in the C double bond C, and it's those electrons that are being donated down to M. So you have a few different metal orbitals that can be used on M, this one being the S orbital, PZ, DZ squared. So you can label these guys if you like on there. And it could be any of these ones here. But it's those electrons that are located in that pi bond that are donated to the metal. And on the other hand, it can also be a pi acceptor, because for each double bond or pi bond, you have a pi star as well, right? So looking at those pi star orbitals, again, you're going to have the proper symmetry that you can have back donation from one of these, like DZY or DZX, into those pi star orbitals, or also from either PX or PY, depending on which direction we're looking here. Okay, so you have a couple different things that can happen. To stop sharing that, and just to get a little bit better of a picture. So if you were to actually try and write this out yourself, you have sigma donation from that, let's say one of these right there. And you're also going to have pi back bonding. So we know we have these filled metal d orbitals, and they can donate back into the pi star orbital. Okay, so those two different situations going on again. Now, the consequence of all of this, you can end up with some back bonding, and do this back bonding, you're going to end up weakening that carbon-carbon bond. So instead of it being a nice strong double bond, in this case, it's going to get weaker and it's going to get longer. Remember kind of what we were discussing with CO and that stretching frequency? If you're giving back into some form of anti-bonding orbital, it's going to weaken the overall bonding situation. And you're going to end up with a decrease in that stretching frequency again. That's what that next point is telling us there. So if you just kind of look, we'll do those two extremes, kind of like what we did with the hydride. If you start with, I'm just going to draw it on that side now. So this guy here, giving electrons. Each of these carbons at this point in time is sp2. Okay? Now, as you start to increase your back bonding, remember, so you're dumping into that pi star orbital, you're still going to have that carbon-carbon single bond. We're getting a similar situation kind of like this. And if you increase your back bonding even more, you're going to get to that point where you've actually broken this bond, you've broken that double bond, and created two new bonds. You've taken it much farther. That oxidative addition step that we looked at. Remember, you have these substituents though on each carbon. They're going to start to get bumped up, and what ends up happening is that now becomes sp3. Okay? So what you've done in this case here is you've made what's called a metallocyclopropane. Okay? So again, that's an oxidative, addition. Okay.